finally. Okay. All right. So this is the last lecture in the spectroscopy series, and IR spectroscopy, which is really common as a secondary methods of analysis. So if you remember from the beginning of the semester, we talked about primary methods of analysis and secondary methods of analysis. Does anybody remember the difference?
Is secondary like something you would do after you already separated the compounds, or like, I don't know. What the, like, depending on if they're accepted by like organizations.
Yeah, so primary methods of analysis, they are accepted by organizations, they are validated, so they're approved by analytical organization. So that's why they're called primary, because so they have been validated, accredited, and all of that. Secondary, they're called secondary not because they're not good, they are calibrated using primary methods of analysis. And usually they're faster methods and used during, processing online for quality control, not for labeling. You cannot use secondary methods of analysis for labeling on the nutrition label, that is. So IR plays a really important role for quick method of analysis during processing, a secondary method of analysis that is fast to check quality. So that's why they're important, and that's why we're spending a lecture on it, despite it really being a little complex to understand from the physics side of things. So I won't focus really on the mechanism. I will focus more on the application. But just to give you an overview, we have two regions that are really important in the IR region, the mid-infrared and the near-infrared. So near, meaning the wavelengths are close to the red in the visible range. So, and they are shorter in length, the wavelength, than the mid-IR that are a little further and they are longer. So the near IR carries more energy or have higher frequency than the mid-IR. So this is something you want to remember. Shorter wavelength, higher frequency, longer wavelength, lower frequency. And then you can do qualitative analysis for a lot of different purposes, and then quantitative for compositional analysis, for example, as a secondary method of analysis. And then interaction of the energy and the matter can be dispersive, can be reflectance, can be transmittance, and some instruments has the capability to do calculations using Fourier transform mathematical calculations for quantification. So these are terms that will come up during the next set of slides. And again, I will focus on differences between mid-IR and near-IR. So this is something you want to know. I will explain the methodology, but not too deep into the physics of the equipment. And then talk about application. Application is important. That's what I want you to learn from here is difference between mid-IR, near-IR, and application. All right, so speaking of application, where do you think, I did mention a couple already, where do you think we use IR? Structure, yes, structural elucidation, identification, that's qualitative, but we use it quite a bit for detection, identification, structure elucidation, very good. Do we do any quantification? Yes. So we can do compositional analysis as a secondary method of analysis. And then we can use it for quality assurance. So these are the applications and the categories of these applications. Okay, so It is a non-invasive technique, so you have limited amount of sample. You can actually run it through your equipment and then reuse the sample because it doesn't burn the sample, it doesn't dehydrate the sample, it doesn't do anything destructive to the sample. And it's very, very quick. And if it's calibrated correctly, it's more or less accurate. And usually you analyze the sample as is. You don't do a lot of sample prep. Sometimes, depending on the equipment you have, you might want to mill the sample, make sure it's homogeneous. But usually there is no sample prep procedures that are extensive. And it's very suitable for routine quick analysis. Very energy efficient, environmentally friendly. Some equipments can be expensive, but once you have the equipment, it's usually very cost effective. Okay, so like what we talked about absorption and fluorescence, you need the source of light, and the source of light hits the sample absorbs light, and then there is a transmitted light or reflected. We'll talk about that. That goes to the detector. Similar principle, the only difference it's IR radiation instead of UV or visible range. So that's pretty much what it is. The cool thing about it is sometimes when you have certain equipment, you can get, or certain type of detectors, you can get a spectra. So you can get transmittance or reflectance over a broad range of wavelengths or wave numbers. In this case, we use wave numbers, and I'll explain wave numbers in a minute. So you get this, that's why it's good for structural elucidation, for identification, for detection of foreign components. So it gives you like a real fingerprint for the component that you're looking for. So the IR radiation is equivalent to vibrational energy. So the energy is not big enough to generate electronic energy shifts. So we don't see shift from E0 to E1. It's much lower energy. Again, IR radiation is in the zone of longer wavelength than UV or visible range. So because they're longer, they carry less energy, and that energy allows shifting in the vibration energy range. So vibration really refers to the bonds within a molecule. The bonds within a molecule can stretch or bend. And I'll show you the image in a little bit. And then upon the energy being released, they vibrate. And that's why it's called vibrational energy. And like with UV and visible, so we can measure the radiation in terms of frequency, so which is related to the energy that these wavelengths carry. Okay, and so it's the same concept, really. And same with electronic energy. So the levels are quantized in a sense. They are allowable levels. They're not on a continuous scale. They're just within every molecule, there are allowable vibrational levels, which is very similar to electronic energy we talked about. So in IR, we talk more about wave number than wavelength. And the relationship is wave number 1 over wavelength. And sometimes people refer to it as frequency as well. So, but in IR, we relate wave number to transmittance, whereas in absorption and fluorescence, we relate absorption or fluorescence to wavelength. That's the difference. That's two important that is, I would say, one important difference. And these are your stretching and bending bonds. So vibration energy only applies to molecules, not atoms, because it relates to the stretching. These are stretching, these are bending in different directions. And then when they stretch or bend and then go back to where they were, that's the release, or that's when they vibrate. That's exactly just all you need to know here, is that they're always in a stretching and bending situation. And then when IR radiation hits them, they will stretch or bend in different direction due to the changes, I would say, in the electron distribution within the bond. Again, I don't want you to worry about that also these kind of details, but I want you to know that when the atoms are released, then they vibrate or go back to the original state, then they vibrate due to the IR frequency. I think I mentioned all of this. And so the vibration or the stretching and bending is really the change in the distribution of electrons, like I said, between the two atoms in a bond. Okay. Now, here where I want you to, pay more attention to, in mid-IR, you get really sharp peaks. And these are, it's opposite to absorption, because here you measure the change in transmittance. So that's a negative there. Because when they absorb light, less transmitted light will reach the detector. So that's why it's downward rather than upward. So it's more negative, because we're looking at percent transmittance. And then here we have wave number, not wavelength. And then what's unique and characteristic about each peak, it relates to the stretching and bending of a specific functional group in a molecule. So if you see, each peak is designated to a different group. And then when we know the transmittance of each functional group at different wave number, we can elucidate the structure or identify the structure of the molecule. In this case, butyraldehyde. So it is used to do structure elucidation and identification by knowing the transmittance or percent transmittance of different functional groups within the molecule. So how is that helpful? Because we have different functional groups, and we know within each functional group what is really absorbing, the stretching and bending of which bond. And then the frequency or wave number, they're the same, is known for every bond within different groups, whether they're alkanes, alkenes, alcohols, ether, all of that. So, and I'll tell you how that's important for quantification in a minute. Okay. True or false? Yes, false. Tell me why you thought it was true.
It's not destructive, so I thought you could.
What's unique about vibration? Can an atom by itself vibrate?
No.
Yes. Yeah, correct. So, yeah.
Wait, I was right?
No, yeah,
you
no,
were,
yeah.
okay.
I'm saying yes, you're right. No. Yes, the answer is no. So yeah, an atom by itself, like in an atomic absorption, you are actually breaking, atomizing your molecules into atoms in the gaseous state, and atoms don't vibrate. They don't have vibration energy. They have electronic energy. So we cannot employ IR when we are in atomic absorption. Okay, so it has to be a molecule made up of multiple atoms in a bond, with multiple bonds. Okay. So there are different types of instrument. Again, I'm not going to focus too much on that, but I just want to say that dispersive instruments are old instruments. They have a monochromator, like same UV and fluorescence instrument, where the light get diffracted into multiple wavelengths and wave numbers, and a singular wave number is selected for determination or quantification. So, and then of course there is a light source that will give you IR radiation, and then the monochromator and different detectors. But this is no longer used. I mean, if you belong to a lab that's a 30-year-old lab, they might still have these instruments. But now currently the instruments that are made and being adopted by the industry are based on Fourier transform. So in Fourier transform, if you remember this image, I showed it to you where we have amplification and cancellation, that's we call interference. So in the unit, you have mirrors, and then you have the directions of the mirror can amplify a specific wave number or wavelength and can cancel interferences from wave numbers that you really don't want to be there, so that you can amplify a signal and reduce interference. So in these type of instruments, they also can do Fourier transform calculations. So all the light hits the sample, and then there will be the light transmitted, and it will give you information about so many different functional groups. And you can use Fourier transform calculation and regression equation to determine, to quantify. So that's an advanced kind of characteristic compared to UV absorption and fluorescence. This Fourier transform allow us to quantitate based on regression calculations and converting all the transmitted light into a measurable spectrum. So very briefly here, there are different types of IR. You have the transmission, mostly for liquid. So you have liquid sample, all the light hits, and then the transmitted gets to the detector and you generate a spectrum. But sometimes you have solid samples. So the solid samples can be mixed with potassium bromide to allow dispersion and also the light to pass through. But most commonly for solids, total reflectance, meaning you have the solid sample, the IR radiation will hit the sample, molecules that absorb light will interact, and the rest of the light will be reflected. And that's why it's called reflectance, not transmission in this case. Internal reflection is for liquid samples. Same thing, it goes in for a little bit, interact with the molecules, and then whatever gets absorbed is absorbed, and the rest of the light gets reflected and goes to the detector. Okay, so you can have IR radiation in line with GC. So for example, you're separating molecule with gas chromatography. The separated molecule can move onto an FTIR and get characteristic information on that molecule using IR. Or you can have microscope with IR, with FTIR. So if you have sample on a microscope slide, and then you can direct a beam focused onto that little bit of the microscope and then give you FTIR spectra. So actually this technology has been used by General Mills to monitor crystallization of sugar in Cheerios. So they see the difference over time and the changes in the crystallization of sugar using microscope interface with FTIR. It's pretty cool. All right, so application. And that's what I want you to focus on, is we can apply Beer's law if we have a select wave number that we isolate and quantitate. We can also quantitate if we're doing FTIR because, like I said, we can use Fourier transform and regression equations to quantitate. And that is the strength of FTIR instrumentation. You can quantitate over a wide range of wave numbers. So Raman spectroscopy, it's a huge component of IR or mid-IR. And it's more frequently used nowadays than before and has high sensitivity, but I'm just going to quickly brush over it. It requires a whole semester to learn Raman spectroscopy, but it is based on scattering of light. So when a light hits, an IR radiation hits the sample, some of that light scatter, where the scattered light energy is equal to the energy of the light that hit. So no information really on the sample. But Raman scattering is when the light hits the molecule and the molecule absorbs some of that energy and the rest of the light is scattered. So the scattered light does not contain the light that was absorbed by the molecule, and that's Raman scattering. That's all I'm going to say about this for now, in this course at least. I lied. There was another slide on Raman. But okay, so the thing that I want to say is applicable to both solid and liquid samples. So there is no interference of water, which is very important, especially that food samples have a lot of moisture content in it. So Raman does not have interference of water, so we can measure liquid and solid samples. Okay, now this is it for Raman. All right, so near IR is so important in food industry as it also, did I skip the application of milk in mid-IR? Where is the milk use of mid-IR in milk? Oh, here, I skipped it completely. Yeah, this is very important in determining the quality of milk during processing. So they use mid-IR to determine fat, protein, and lactose in milk. And protein or fat, they measure the vibration of carbonyl carbons. In protein, they measure the vibration of the amide groups in protein. And in lactose, they measure the vibration of hydroxyl or OH groups. And so IR milk analyzer is very, very common for determination of quality of milk. Incoming milk that is used in different food products, they run it through IR that is calibrated. So the calibration happens by determining fat, protein, and lactose using official methods of analysis. And then what they do, and actually we used to take food analysis students touring. We used to take them to a company, and I can't remember, I don't think it got sold to Eurofin. Before Eurofin, there was a company, I forgot what it's called, but Eurofin bought it. So I used to take the students there and they would see the IR in action, and they actually produce milk with different fat concentration, protein concentration, lactose concentration. They use it as standards to calibrate the equipment. So basically you prepare 5 different milk samples with 5 different concentration of protein or fat or lactose. And then you measure fat by Moijner method or Moijner. You measure protein by Kaldal. You measure lactose by the lactose assay, and then you calibrate the equipment at different concentrations. And then once it's calibrated, you can screen a lot of samples coming in. Yeah, this is important. And I kind of brushed over it, forgot to mention, but this is important. All right. Now, near IR is also very important. It's in processes like flour milling in mills. So when, in order to check the quality of the flour, whether it's whole wheat flour or refined flour, so if they want to determine if the refining process was proper, they measure composition analysis, especially ash content, for example, protein, ash, fat, all of the composition, and determine that, okay, they got 100% refined or 50% refined, depending on the flour that they are producing. And also it is calibrated with standards that have different concentration. So they can have flours with different amount of bran in it. So it's naturally will have different compositional components, and they will calibrate the NIR. And then it's very easy. You just have to make sure that it's a homogeneous sample put into the sample cup, and then you would measure the IR, and it's instantaneous, almost giving you the concentration of fat, ash, protein, etc. So mostly it's diffuse reflectance technique. So for solid foods, so basically you have your flour. I'm giving you the example of flour. Go ahead.
And you put the sample in and you're looking at like the analysis, does it give you different fingerprints for each compound, or is it all on the same spectra? Like, so you have to analyze like all the protein, the fat.
Yeah,
whatever
it gives you, I'll show you a figure. It gives you a whole spectra, and then there are regions that would be, this is the region for protein, this is the region for lipid, this is the region for water. So it gives you a region that, you know, as an analyst, you can select and then quantitate. The IFT, IR, well, Fourier transform calculator. Yeah, but it happens very quick. It just gives you number. You can choose to see the spectra, or it just gives you the percentage. It's calibrated, it just gives you the percentage. It's pretty cool, and it works with diffuse reflectance, meaning the vibration or the light, IR light, goes into the sample, and then the light that does not get absorbed gets reflected and goes to the detector. So there is the light that gets reflected right away without going in. It's like a mirror, it gets reflected. And then the light that goes actually in, and the molecules absorb some of that light, and then the rest of it gets reflected, directed to, by mirrors, directed to the detectors. And that's exactly what I said about some of the light diffuse, and the molecules absorb the light, and then you get the fingerprint. So the bands in near IR are not sharp. They're overtuned, so like hills. But we know where to look for different functional groups. So whether we're looking at proteins, lipids, or carbohydrate, we look at the vibration of a bond that has a hydrogen and a carbon, or nitrogen, or oxygen. So for water, we look at two regions. For OH stretch, for NH stretches, for protein, for lipid, methylene stretches, and methyl stretches, and also carbohydrate, CO, and OH stretches. And this is the whole spectra, Ali, that you were asking me about. So we know that water is here and here, and in cheese, you have a lot of water. So you see large peaks for water, whereas for wheat and egg white, you don't have those water peaks. It's just a visual of how the spectra looks like. So I wouldn't worry about radiation source. We just use sources that provide us the IR radiation. We can have a monochromator, but usually an interferometer is used, where all the radiation gets analyzed, and we use Fourier transform technology and regression analysis to get quantification. So reflection is for solid sample and transmittance is for liquid sample. So we can do both in an IR, and then we can either have qualitative or quantitative by regression analysis. And this is an example application for detection of an adulterant, which is melamine. So this would be a pure melamine IR spectra, and then this is an infant food, and infant food also got adulterated by melamine. So if we see some of these characteristic peaks here, for example, in infant formula, then we say, okay, this is adulterated. So like I said, it's widely used in grains, cereal products, oil, seed, and also in dairy. But calibration is key. So see that key is all in caps. Has to be calibrated as it is considered a secondary quantification technique. So I'm almost done here. Can NIR be used for online measuring of constituents during processing? Yes, yes, that's all what we were talking about. Yes. But it has to be calibrated with official methods of analysis. These are just FYI, the advantages and limitations, and that's it. We're done. Okay. Focus on application, difference in weight in NIR and mid-IR, not so much on the instrument. And yeah, reflectance or transmittance. That's why I'm telling you what to focus on.
Okay.
Yeah. Yep.
Is it not instructive? Or
It's not, no.
both of them are not
No,
instructive?
the sample, nothing happens. Light goes through it, and then you can take the sample and do more work with it. All right, thank you guys, and good luck. If you need anything, you can email me throughout the weekend. And Gray and who else will be there other than you, Gray? The TAs. You don't know? Okay. Well, we know that Gray is gonna be there. Yes,
So I know when we did the.
can I stop recording? No, so that you're not.
uh,
Bye.